Section 12.4, we're going to be doing inverse operations of the exponents. So the idea is, when I ask what's the inverse operation of exponents, a lot of times people will go, oh yeah, you know, to undo a second power, we do a second root. To undo a third power, we do a third root. I'm like, okay, but what happens when x is the exponent? See, and we just had that in our last section. We had x as an exponent. How do we undo that? You can't do like an xth root of something, right? So we need an inverse operation that undoes that, and that's called logarithms. Okay, so it is the inverse operation of exponenting. I don't even know if that's the word, but it's kind of like x is the exponent, and so we need to be able to undo it. Here's our goal. I've got 2 to the x equals 5. In the previous section, we're like, well, yeah, that's easy. Just make them both the same base. Okay, so you tell me how you're going to make 2 and 5 the same base. They're both prime numbers, right? So we need something else to undo this x up here as an exponent, and that's what we're going to learn. When I say log base b of x equals y, that to me is utter nonsense. And people will go, oh my gosh, this is why I don't like logarithms. This is utter nonsense. And I go, okay, well then you just need to learn how to read it. Because when I see log base b of x equals y, I literally say b is the base, x is the result, and y is the exponent. This to me says b to what power y makes the result x. B to what exponent makes x. Okay? Real quick, just the argument I always make for this, because I want to make sure people are looking at me like, okay, that still seems crazy to me. If I was to ask my 6-year-old daughter, hey, what's the square root of 25? She would like go, I have no idea what you're talking about, right? She maybe has a brief understanding of multiplying and dividing and cutting things up, but whatever, she's not able to say the square root is 5 because she has no idea what square root means. See, I ask you guys, what's the square root of 25? And you're like, 5, because 5 times 5 is 25. Awesome. When you hear somebody say, what is the square root of something, in your mind automatically translates to that to what number times itself makes. And you're like, yeah, square roots are now easy. Logarithms can be that easy. You just have to learn to translate and read what they actually mean. When I, for instance, log base 3 of 9 is y. This to me says the base 3 to what exponent? That's our y. Makes 9. 3 to what power makes 9? Shoot, y is 2. How do I know that? Because 3 to the second power makes 9. See, if you can learn to read them with meaning, just like you learned how to read square roots with meaning, then these don't become difficult. Log base 3 of 81 is y. Seems like utter nonsense. But if I read this as 3 to what power makes 81? Well, that would be 3 to the 4th power. Log base 3 of x is 3. You should be getting good at these by now. 3 to this power makes x. So this is literally saying x is 3 to the 3rd. Our base is 3, our exponent is 3. X is, the result is, the base to the exponent. X is 27. How do I know that? 3 to the 3rd power makes this result 27. Just a different way of thinking about it. Okay? What we're really doing when we're writing these out in sentences and making sense out of them is we're translating from logarithmic form to exponential form. So log base b of x equals y is the same thing as saying b to the exponent y equals the result x. In both of these sides, b is the base, y is the exponent, and x is the result. So let's just take some things and let's rewrite them, because this has log base 1/5 of 25 is -2. We're going to rewrite that in exponential form. What is the base? Well, that's the b. So 1/5 raised to the, what is the exponent? The exponent is that y on the other side, so 1/5 to the -2 is the result 25. And that is true. Log base 4 of 1/64 is -3. Okay, let's rewrite that. What is the base? Base here is 4, base here is 4. Raised to the, what's the exponent? Is equals what result? The result is 1/64. So there are times when you want to be able to go from logarithmic form to exponential form, and there are times where you want to go back the other way. Let's keep going. 3 squared is 9. I feel pretty confident about that. Could you write that as a logarithm? Log base what? What's the base in 3 squared equals 9? Well, the base is that 3. The exponent or the result? What goes inside the logarithm is the result. What goes on the other side is the exponent. What was the exponent? 2. These two things say the same thing to me. Log base 3 of 9 equals 2 seems utterly nonsensical to me. But I know it also says 3 squared equals 9. They say the same thing. This one, log base what? Well, the base here is 10 of what result? 10,000 is what exponent? 5. Now we wouldn't write it like that. You can, but log base 10 is known as the common log. Think about it this way. Most of the modern world, we live in a base 10 number system. America's a little weird where we start doing like 12 inches in a foot and all that, but we count with 10 fingers, 10 toes. We live in a base 10 number system. That's kind of a common base. So if the base is 10, you actually do not need to write the base. You could just write log of 10,000 equals 5. And when you leave this empty, there's an assumed base 10. Just like when I do a square root, there's a little assumed 2 because it's the second root. Just like when there's an x by itself, there's an assumed 1x. If we don't put a base, it is base 10. Common log. So let's rewrite this. Log x equals 2. What's the base? We just said, if there is no base, the base is 10. So let's rewrite this. The base, 10, to what exponent equals x? X is equal to 100. Log base 10 of 100 would equal 2, because 10 squared makes 100. What do I do here? This one's a little more complicated. Well, rewrite it. Logarithmic form, our base here is 2, so 2 to the exponent, 4th power, is equal to the result. Well, hey, we can solve that. 2 to the 4th, I believe, is 16. We add. So 3x is equal to about 18. And when we divide, x equals 6. This one looks a little scarier. What's our base? What's our exponent? What's our result? There are two ways to approach this. One is what I think most of you would do, and the second one is a little more advanced, which you're going to need if you're going into the trigonometry pre-calculus direction. And the advanced way requires some more advanced thinking, and the whole reason we do it, though, is because it saves us steps. It's actually easier to do. But worst case scenario, if you looked at this, you should all go, well, hey, a negative exponent, not cool. I'm going to make this what? 1 over m to the 4th is equal 1 over 16. I do not like solving this with an m to the 4th in the denominator, so I would need to multiply both sides. It's also, we kind of call it cross-multiplying, but if I multiply both sides by both denominators, so 16 m to the 4th, 16 m to the fourth. On the left side, the m to the fourth cancels. On the right side, the 16 cancels. Sorry, m to the fourth. And so what we end up with is 16 is equal to m to the fourth. How do I undo a fourth exponent? With a fourth root. So that m would equal 2. Algebraically here, we'd actually get plus or minus 2. But this is actually a good time to note that the base, good news is the base will always be positive. So just keep the positive 2 there. Even though algebraically we get a plus or minus, the negative 2 is extraneous. Why don't we have negative bases and exponents? Because we don't need them. Like, we could just do it, but we don't do math for the sake of doing math. We don't need a negative exponent, or I'm sorry, a negative base. So the negative 2 is extraneous. Like I said, so that's one option. That's not actually how I would have solved this. You're like, really? Yeah, I would use the rules of exponents. See, I'm good at that. That's something you need. You need to be really good at those for your trigonometry and pre-calculus. I really just want this exponent to become positive. I know that I can raise both sides to a power that will make that a positive exponent. Here's all I would do. I want to multiply this negative 4 and make it a positive 4. So I'm going to raise both sides to a negative exponent. Why would I do that? The power rule says m to the negative fourth to the negative 1. These multiply, become m to the fourth. 1/16 to negative 1 is 16. Then I still would do my fourth root, so that m is equal to plus or minus 2, just the positive 2 this time. It's a little less work, but it requires you to know a little more about your exponents, be a little more comfortable with that, okay? Like I said, both get you the same answer. The right, I would expect you to be able to do if you're in a pre-calc class. Let's keep going. So here's what we just said. The good news about logarithms, the bases are always positive. This also means that if I have log base b of x equal to y, if the base is always positive, then a positive to an exponent, the result will also be always positive. Because a positive number raised to an exponent will never just become negative. So both the bases are positive, and the result, the value inside the logarithm, must also be positive. Here's some simple, kind of check the rules and see if we can understand this. Log base 6 of 6 equals. See, this time, I'm trying to solve for this over here. Once again, if you can read this, this is basically saying 6 to what power makes 6? 6 to what power makes 6? That would be 6 to the first power. And you can always check it that 6 to the first power is equal to 6. This gives us kind of a general rule. If I have log base b of b, b to what power is b? If the base and the results are the same, the exponent will be 1. What about log base 8 of 1? Some of you are like, I already know this answer. Because you can read, you're starting to learn how to read logarithms. 8 to what exponent makes 1? 8 to what exponent makes 1? That would be 8 to the 0 power. So if I have log of any base, if my result is 1, the base raised to the 0 will make 1. Whenever there's a 1 as my result, the answer will be 0, because anything to the 0 power makes 1. Log base 3 of negative 3. 3 to what power would make a negative 3? Somebody's like, negative 1. No, that would be 1/3. See, if I raise 3 to a power, 3, 3, 9, 27, 81, it's not going to turn negative. If I take it to a negative exponent, 1/3, 1/9, 1 over 27, it's never going to become negative. This has no solution. And why is it no solution? Because a positive base, remember we said the bases are always positive, will never become a negative result. So log base b of a negative is not real. Log base b of 0 is not real. Why does that work as well? Because if I raise 3 to a power, it will never become nothing. You're like, what about 0? We just did that. Anything to the 0 power would make a 1. Okay? So you can never, inside the logarithm, you can never have a negative and you can never have a 0. We're going to graph log base 2 of x. There are two ways of doing this. See, logarithms are the inverse of an exponent. I told you that already, so you can just believe me on that, but I'm going to also prove it. But here's an option. This is not my favorite way of graphing this, but you can do this. Can you graph 2 to the x? And you're like, yeah, we just did that. That was easy, right? 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. Going to the left, you got 1/2, 1/4. This would be 2 to the x, right? Well, we just said logarithms are the inverse of that, right? How do we graph an inverse if I know the other graph? We take x and y and we flip it. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And 2, 4 becomes 4, 2. Negative 1, 1/2 becomes 1/2, negative 1. Negative 2, 1/4 becomes 1/4, negative 2. This is what a logarithm looks like. And notice they are parallel across the line y equals x. There's symmetry. So that's one option. I think that's kind of a cheap way out because I think you should be able to graph logarithms by just checking powers of the base. See, I can plug any number in there, but I want to go 2 to what power makes? 2 to what power makes 5? We already said that's not going to be fun, so I'm not going to solve it that way, right? So what I'm going to do is I'm going to pick powers of the base. I'm going to pick 2 to the 0, I'm going to pick 2 to the 1, I'm going to pick 2 squared, 2 to the third, 2 to the... Because what's going to happen? 2 to the 0 is 1. So what is log base 2 of 1? 0. 2 is another easy one, right? Because what is log base 2 of 2? 1. What about 4? What is log base 2 of 4? What is log base 2 of 8? Right? 2 to what power? Basically, whatever the exponent is what the y equals. We can also do the 1/2, right? We said 1/2 log base 2 of 1/2. 2 to what power makes 1/2 would be negative 1. Log base 2 of 1/4 would be negative 2. These are basically all the points we just plotted. What? 1, 0, 2, 1, 4, 2, 5, 6, 7, 8 before it goes up to 3, right? So I can keep going on this. The next one would be 16, 4. And then the idea is on this side it gets closer and closer to 0. So you got two options. You can graph the exponential and then flip the points, or check powers of the base. Why do I have this negative 1 and 0 here? You have to remember there's a restriction on the domain here. See, when I look at this, I cannot put a negative 1 or a 0 inside the logarithm. This is not a real point. So we don't graph negative 1 and 0. In fact, look what happens here. On the 2 to the x, our domain is left forever and right forever. On our log base 2 of x, right, the domain on the 2 to the x was left and right forever. Over here, the range is up and down forever. Is all real numbers. On the 2 to the x, the range was y was greater than 0. Over here, the domain will be that x is greater than 0. What happens is what? The domain and the range flip. Anyway, we'll do another example of this just to kind of help understand. Let's just graph log of x. You're like, where's the base? Got to remember, if there is no base, this is base 10. So what numbers am I going to check? I'm not going to check 0 and 1. We already said there's going to be a restriction. X has to be greater than 0. So rather than graph 10 to the x, if you want to do that and flip the points, you can. I'm going to check powers of the base. So I'm going to check 10 to the 0, 10 to the first, 10 to the second, and just for fun and giggles, 10 to the negative 1. I'm going to check 1, 10, 100, and 1/10. Why? Because I can do log of 3, log of 5, but I want easy numbers. And so by checking things that are base 10, then I end up with something like this. What is log of 1? 10 to what power makes 1? What is log of 10? 10 to what power makes 10? What is log of 100? 10 to what power makes 100? See, I got three nice easy points. And the 1/10, 10 to what power makes 1/10 is negative 1. I can graph these points. 1, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10 before it gets up to 1. It won't get up to 2 till all the way over at 100. This graph is increasing very slowly. What happens here between negative 1 and 0? Well, those are our fractions, right? That means the exponents must be negative. That's where it gets closer to 0. That's a quick sketch, okay? So that is it for section 12.4. Get studying, and we're almost done with this. Should be a pretty easy chapter.